essentially what happened before the Big Bang. Right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it, because we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation.
Have you ever wondered what existed before the Big Bang? Was there truly nothing, or was there something even more astonishing lurking in the depths of pre-universal existence? Brian Cox, a leading voice in the field of astrophysics, has explored these questions and more. Today we'll unravel the mysteries of the universe's origins and discover what might have come before the Big Bang. Join us as we explore the terrifying and fascinating possibilities that Brian Cox and other leading scientists propose about the universe's beginnings. Before the Big Bang, scientists find it difficult to answer the question of what existed before the Big Bang, but current theories offer some intriguing insights. To solve this, it is critical to comprehend the Big Bang itself. The Big Bang is defined as the moment when the cosmos became incredibly hot and dense. From this point, the cosmos expanded and cooled, eventually forming the galaxies, stars, and other structures we see today. Before the Big Bang, the cosmos looked very different from what we know now. According to the inflation hypothesis, prior to the Big Bang, the universe was chilly and almost empty. During this epoch, the universe saw immense expansion at an astounding rate. This fast expansion, known as inflation, eventually slowed and ceased in certain areas. The energy fueling this expansion then expanded out, heating up the universe and forming the particles that make up everything we see. This process is referred to as the Big Bang. Eternal inflation takes the concept of what existed prior to the Big Bang a step further. According to this idea, inflation occurred more than once and will continue indefinitely. This model depicts the universe's fabric stretching out, slowing down, and coming to a halt in various locations. Each of these places then has its own Big Bang, creating a new universe. This gives rise to the concept of the inflationary multiverse, in which there are numerous worlds, each with its own Big Bang, resulting in an infinite, fractal-like structure of multiple universes. In the immense universe, the concept of total emptiness is more theoretical than real. Even if we removed all energy from the universe, it would not be completely empty. Our cosmos is made up of many different components, including matter, radiation, antimatter, neutrinos, dark matter, and dark energy. Even in the absence of traditional energy, new types of energy may emerge. This shows that the cosmos does not fully understand the concept of total emptiness. One might think that removing all energy would result in a state of absolute zero in the full absence of particles. But this is not the case. Even in an empty universe, the expansion would generate radiation. This means that the cosmos is never totally empty, even before the Big Bang. The concept that the cosmos sprang from nothing is both exciting and confusing. Evidence implies that something always exists, even when all particles, antiparticles, and photons are eliminated. Even if we cleared a space of matter and energy, eliminated external electromagnetic and gravitational fields, and prevented photons or gravitational waves from entering, there would still be a type of physical nothingness. Quantum fields and fundamental constants would persist, with a finite non-zero value for zero-point energy. This zero-point energy is the closest approximation to nothing in our cosmos. Zero-point energy is the lowest level of energy found in a vacuum, even when it appears empty. This concept of almost nothing is important since real nothingness, which lacks energy and particles, cannot exist in our universe. Scientific principles demonstrate that something always exists, making the concept of pure nothingness impossible. The constant presence of something, even in a vacuum, continues to fascinate scientists. The universe is far from empty. It contains a wide range of substances and events, including stars, gas, dust, galaxies, quasars, cosmic rays, and radiation emitted by stars and the leftovers of the Big Bang. As observational tools evolve, we may detect new signals, such as gravitational waves from moving masses or enigmatic signals from dark matter. These findings could shed more light on the nature of black holes, both active and dormant. Everything we see happens in a universe that is always evolving. The fabric of our cosmos, also known as space-time, is growing. This expansion implies that if you pick 2 points far apart in space-time, the space between them grows over time. Furthermore, the time it takes for light to travel between these places increases, and the wavelength of light spanning from one point to another grows longer. This continuing expansion is an essential part of our cosmos. Understanding the universe's evolution on such a large scale reveals important insights into its dynamic nature. The universe is not static, but rather evolving. This constantly changing element of the universe is critical for understanding its history and fundamental workings. Expansion and cooling of the universe. As the universe expands, it undergoes two significant changes. It grows larger and becomes colder. As the universe expands, light extends to longer wavelengths. When light extends, its energy lowers, resulting in lower temperatures. This suggests that the early cosmos was extraordinarily hot, but is gradually cooling as it expands. In the distant future, the cosmos will become far colder than it is today. As the universe expands, objects with mass or energy tend to attract one another. This gravitational force causes the creation of clusters in a large cosmic network. Imagine removing all matter and radiation from the universe, leaving only what appears to be empty space. However, this empty space would continue to expand and be regulated by physical rules. It would be influenced by the quantum fields that exist across the universe. Despite the apparent emptiness, this place adheres to specific physical principles. Dark energy would exist even in this imagined cosmos, devoid of matter and radiation. Dark energy, together with the zero-point energy of quantum fields, shows that even in an empty world, some type of energy exists. This is because in a cosmos rich in dark energy and quantum fields, zero-point energy would not be truly zero. The universe would still contain energy that could not be converted into mechanical work. As the cosmos expands and cools, radiation will eventually become the main type of energy. This radiation would outperform other forms of matter and energy. In the far future, dark energy will have the greatest influence on the universe's behavior. Looking back in time, before the fiery Big Bang, cosmic inflation was the main force in the cosmos. During this time, the cosmos expanded at an exceedingly rapid and consistent rate. The universe was dominated by inflationary energy, not matter or radiation. This energy was akin to today's dark energy, but considerably more powerful, causing the cosmos to expand at a significantly faster rate. If the concept of everlasting inflation is correct, it means that the cosmos may not have had a single origin. Alternatively, there could have been an unending succession of expansions. To completely comprehend the origins of our world, we must examine three fundamental concepts: the hot Big Bang theory, cosmic inflation theory, and the question of whether the universe had a true beginning. Several significant discoveries were made in the early 20th century that helped influence our knowledge of the universe. Alexander Friedmann utilized Einstein's theory of general relativity to demonstrate that a cosmos filled uniformly with matter and energy cannot be static. It must expand or contract. The rate of expansion or contraction is determined by the overall energy density of the space. Henrietta Leavitt produced a groundbreaking observation about variable stars. She established a relationship between their brightness and inherent luminosity, known as the period luminosity equation. This was an important piece of the puzzle for understanding the universe's scale. Vesto Melvin Slipher made observations that indicated variations in light from galaxies. He discovered that these galaxies were traveling away from us at incredible speeds. Edwin Hubble and Milton Humason later found similar sorts of variable stars in spiral and elliptical galaxies. They confirmed the existence of these galaxies by measuring their distances from our own. These observations lead to the hypothesis that the universe is expanding. If the cosmos is growing, space will lengthen over time. Space expands and the substance within it gets less dense. Radiation, such as light waves, thins out and stretches. This process causes the cosmos to cool. If we envision reversing this process, we can conclude that matter and radiation were formerly more concentrated and hotter. Understanding these principles helps us understand the nature of our universe and how it evolved. The universe's expansion, radiation cooling, and the influence of dark energy and quantum fields all contribute to the cosmos' dynamic nature. These concepts are critical for comprehending not only the universe's current condition, but also its history and future. Challenges to the Big Bang theory. In the early cosmos, everything was extremely hot and dense. If we could go back in time, we'd see that all matter and radiation were compacted into a very small space. This compression implied that the universe was extremely dense. The light we see now, which has stretched out as the universe has expanded, would have had a considerably shorter wavelength back then, indicating hotter temperatures. To visualize this, consider going back as far as possible. You would arrive at a condition in which all matter and radiation were concentrated into a single point with limitless density and temperature. This concept is fundamental to the Big Bang theory. This hypothesis allows for several significant predictions about the early cosmos. First, the Big Bang theory states that the cosmos should be expanding. This is demonstrated by examining faraway galaxies that are moving away from us in the redshift of their light. This redshift indicates that light waves are stretching out, supporting the idea of an expanding cosmos. Second, the early cosmos should have been rather uniform. In other terms, it should have had an even distribution of matter and radiation. As the universe expanded and cooled over time, structures like stars, galaxies, and galaxy clusters emerged. Initially, the universe was so hot that stable neutral atoms could not exist. This resulted in the prediction and later observation of the cosmic microwave background radiation, which is still detectable today. This background radiation is a leftover from the universe's early hot phase. Third, atomic nuclei were unable to form stable structures in the early stages of the cosmos due to tremendous temperatures. This meant that only light elements such as hydrogen, helium, and lithium and their isotopes could be produced. The cosmos was so hot that neutrinos, which are extremely light and weakly interacting particles, played an important role. Recent observations have proven the existence of cosmic neutrinos, which have detectable impacts on both the large-scale structure of the cosmos and the remnant radiation from the Big Bang. Since the mid-1960s, when cosmic microwave background radiation was discovered, the Big Bang theory has been the primary explanation for the early cosmos. However, as data mounted in the 1960s and 70s, some issues arose that the Big Bang theory could not adequately answer on its own. Three fundamental issues with the Big Bang theory stand out. The first is the horizon problem. When we look at different parts of the universe, we notice that they have fairly similar temperatures and densities. According to the Big Bang model, these regions should not have been able to exchange information or reach thermal equilibrium because they were too far away. This begs the question of how these remote locations came to have such comparable temperatures and conditions. The second obstacle is the flatness problem. In an expanding cosmos, there is an ongoing fight between expansion, pulling things apart, and gravity drawing them back together. Surprisingly, our cosmos appears to be perfectly balanced, with no signs of excessive curvature. The question is, why does the cosmos have such precise flatness? The third issue is the monopole problem. If the cosmos experienced severe temperatures and energy conditions in its early phases, we would expect to see unusual particles like magnetic monopoles and right-handed neutrinos. These particles should be detectable now, but we don't see them. This mismatch implies that the early universe's conditions may not have resulted in their genesis as envisaged. To solve these issues, scientists looked for a fresh explanation. In 1980, Alan Guth suggested a novel concept known as inflation. He proposed that during the very early universe, there was a period of rapid and exponential expansion. During this inflationary phase, the cosmos expanded so swiftly that its energy was not divided between matter and radiation, but was an inherent part of space itself. Inflation provides remedies to three major issues. In the context of the horizon problem, inflation explains how all regions of the universe were once close enough to exchange information. During inflation, the universe's rapid expansion pushed these regions apart, making them appear uniform despite their distance. Concerning the flatness problem, the inflationary theory argues that the cosmos was stretched so far that any initial curvature was flattened out. As a result, the observable cosmos seems flat, regardless of its original shape. In the monopole dilemma, inflation keeps the cosmos from reaching extremely high temperatures, which would result in exotic particles such as magnetic monopoles. Because the cosmos expanded so quickly, it escaped the circumstances required for the production of these particles. The inflation theory. Inflation theory gives a compelling explanation for various cosmological events and serves as a viable alternative to the standard hot Big Bang hypothesis. The idea addresses the question of how the early cosmos, which was initially uniform and isotropic, could have retained these characteristics following inflation. Essentially, inflation is a quantum phenomenon that introduces the initial defects or seeds of cosmic structure, which eventually evolve into the complex structures we see in the universe today. In the 1980s, inflation theory produced several precise and testable predictions about the development of cosmic structures. These predictions were intended to be detectable in both the cosmic microwave background and the large-scale structure of the cosmos. Observations from the 1990s to the current day have confirmed these forecasts. The observed defects in the CMB, including density and temperature changes, correspond to the virtually scale-invariant spectrum predicted by inflationary theory. These abnormalities are fully adiabatic, which means they are caused by fluctuations in density rather than temperature changes, and they occur on sizes greater than what could be produced by signals traveling at the speed of light in an expanding universe. One important finding from inflation theory is that it avoids a singularity problem associated with the traditional hot Big Bang model. Inflation suggests a rapid expansion of space rather than a singularity, an infinitely small and dense point in the early cosmos. This expansion offers an alternative explanation for the universe's origin. Rather than time and space evolving gradually from a single point, inflation implies that space expanded quickly, leading straight to the Big Bang. This raises basic problems regarding whether the concept of a true beginning of the universe has significance within the context of inflation. Without inflation, we would return to a solitary state in which the universe's size approaches zero over a finite period of time. However, because inflation involves exponential expansion, identifying a singularity is difficult, as attaining a state in which the universe has no size would take an indefinite period of time. Furthermore, observable evidence for inflation, such as quantum fluctuations, only covers the last one attosecond before the hot Big Bang. This means that if we were looking for clues regarding a previous major event, inflation offers a hurdle because there are no visible signs of what caused inflation. Eternal inflation is a very intriguing element of inflation. When investigating how inflation works, practically any model that correctly tackles the concerns with the initial Big Bang and generates the quantum phenomena required to launch the universe with defects leads to a scenario in which inflation persists in places beyond our own observable world. While inflation ends in certain regions, such as the one we live in, it continues in numerous others, providing more room that continues to expand. Essentially, once inflation begins, it erases all previous information and continues eternally into the future. In some circumstances, quantum fluctuations, comparable to those that shape the universe's structure, force inflation to end in some locations, resulting in hot Big Bangs. However, the regions where inflation stops are significantly fewer than those where it continues permanently. It is vital to note that no two distinct regions with Big Bangs will intersect because the universe's expansion separates them. Despite its attraction, eternal inflation has limitations. It is eternal only for the future, not the past. According to research, inflationary spacetime does not extend indefinitely into the past and must have arisen from a previous non-inflationary state, which could be single. The problem of past time incompleteness cannot be answered by contemplating alternatives like bouncing or cyclic cosmologies, which have comparable issues in extending into the past. This does not necessarily indicate that the cosmos began with a singularity. However, that is one option. It is also possible to simulate inflation in spacetime by combining an increasing exponential expansion rate with a constant rather than relying simply on exponential growth. This technique allows for a model in which the hot Big Bang, while still the most accurate depiction of the early cosmos, is not the absolute beginning. There is a limit to how far we can extrapolate the temperature and density of matter and radiation throughout the universe. Concept of cosmic inflation. Before the scorching Big Bang, the cosmos experienced cosmic inflation. During this time, the cosmos was dominated by energy and lacked matter and radiation. This energy-filled region grew at an exponential rate, dramatically growing in size. However, inflation cannot continue indefinitely. It had to move from a pre-existing, non-inflationary condition. But our grasp of that earlier stage is limited. We only know that it couldn't have looked exactly like the universe we see now. We live in a universe that is more than just a huge vacuum with matter floating through it. Instead, our cosmos is filled with energy fields that interact to form everything we see. The thought of an empty nothingness can be very disturbing. For example, when actor William Shatner went on a space mission at the age of 90, he intended to discover the universe's greatest mysteries. Instead, he met a dark, chilly abyss, unlike anything on Earth. This vacuum was enormous and all-consuming. However, he didn't notice a true void. What he was truly seeing was a vacuum filled with invisible activity. Quantum field theory is one of the most exact theories in physics, and it can help us understand this idea. It is well known for its ability to accurately anticipate many experimental outcomes. According to quantum field theory, the universe is not made up of matter floating in space. Rather, it is packed with energy fields that extend throughout space and interact with one another. These interactions are responsible for the creation of the entire universe, including ourselves. Physicists explain these energy fields in many ways. Some compare them to fluids such as pool water. Others compare them to a space with different degrees of energy, such as a field of scattered heat. These fields are continually changing due to quantum fluctuations. Quantum fluctuations are transient shifts in energy, similar to ripples on a water surface generated by external factors. These fluctuations stimulate the particles within the fields. An electromagnet, for example, has the ability to change the electromagnetic field. Even in their lowest condition, known as the vacuum state, fields are active. They generate pairs of positive and negative particles that temporarily borrow energy from the vacuum, emerge, and then vanish, returning the energy. These transitory particles are referred to as virtual particles. When a field is energized or achieves a greater energy level, it generates ripples or waves, which result in elementary particles. These particles endure and interact with one another, resulting in the complex structures we see in the universe. The specific field determines the type of particles created. Different matter particles are associated with different kinds of fermions. Electrons, up quarks, down quarks, and neutrinos are essential components of all atoms. These fermions interact using three different sorts of fields. The electromagnetic field involves photons, the strong nuclear force involves gluons, and the weak nuclear force involves W and Z bosons. According to David Tong, a theoretical physicist at Cambridge, without these force fields, matter particles would drift aimlessly across the universe with no interactions or fascinating behavior. Force fields play an important role in particle structure and interactions. Another important field is the Higgs field. Tong compares it to molasses scattered across the universe. The Higgs field gives mass to other particles, preventing them from traveling at the speed of light. This comparison is not perfect since it assumes friction, but in fact, particles interact with the Higgs field in a variety of ways without experiencing genuine friction. All fields, including those relating to matter and forces, exist everywhere but interact differently. Some particles in these fields avoid one another, but others interact, resulting in a variety of reactions and complicated formations. The collaboration of these areas supports everything we know and see in the universe, as well as much that is unknown. Atoms have an intriguing role in particle production. For example, an atom forms when the quark fields have enough energy to make quarks that are not annihilated by antimatter particles. The exact reasons for this are not entirely clear. Gluons, which are related to strong nuclear interaction, combine two up quarks and one down quark to form a proton. The protons and neutrons then combine to form atomic nuclei. Physicists propose that the observable universe is made up of remains from the ongoing birth and destruction of virtual particles. However, dark matter particles provide a distinct issue. These particles do not easily fit into our present understanding of matter and fields. The existence of dark matter remains one of the most pressing issues in modern physics because these particles do not interact with light or other types of electromagnetic radiation in the same way that regular matter does. This makes them tough to identify and research. Concept of nothingness. The universe is replete of virtual particles, but this does not completely erase the concept of emptiness. To understand this, we must investigate numerous conceptions about the nature of the cosmos, beginning with the concept of emptiness that existed before the Big Bang. Before the Big Bang, there existed a condition of emptiness that is still poorly understood. This emptiness was not a void or an empty space, but a vast expanse of quantum energy fields. These fields are not composed of particles or matter, but they are fundamental to the universe's structure. Despite the presence of these quantum fields, they appear to be capable of producing matter and forces, ultimately leading to the formation of the cosmos we see today. Physicists are currently investigating why some fundamental particles survived the Big Bang. Lawrence Krauss, a theoretical physicist, discusses this topic in his book, A Universe from Nothing. Krauss contends that the fundamentally unstable nature of emptiness can result in the production of elementary particles. According to Krauss, fluctuations in what we call nothingness, essentially quantum fields in their lowest energy state, can produce particles. This viewpoint holds that the vacuum itself is a fruitful field for the formation of matter and energy. Another intriguing thought is the vacuum genesis hypothesis. This idea proposes that the cosmos arose from a substantial fluctuation within the nothingness that existed before it. According to this theory, the cosmos began as a massive quantum fluctuation, a sort of bubble in the fabric of nothingness that eventually developed into the universe we observe today. While this idea is still theoretical and has yet to be validated, it offers an intriguing viewpoint on how the cosmos could have formed from what looked to be an empty state. Despite these intriguing possibilities, the concept of a wholly empty cosmos contradicts our understanding of physics. According to physical rules, a fully empty world cannot exist. As long as there is energy, such as the zero-point energy of the quantum vacuum, there will be some type of radiation or activity. Zero-point energy is the energy that remains when a quantum field is at its lowest conceivable energy level. This energy causes the ongoing synthesis and destruction of virtual particles, implying that the universe is never fully inactive. In other words, even if we picture a cosmos free of matter and radiation, quantum mechanics teaches us that the vacuum is not actually empty. The vacuum is a dynamic field with constant energy fluctuations. These oscillations can produce virtual particles, which exist briefly before disappearing. This continual activity assures that the universe is never totally empty, and thus lends credence to the theory that the universe is always filled with some type of energy. Additionally, dark energy plays an important function in this context. Dark energy is a mysterious kind of energy thought to be responsible for the universe's accelerating expansion. Its existence indicates that the cosmos is always expanding, and as long as dark energy exists, the universe will never be fully empty. The presence of dark energy introduces a constant source of energy and growth, contradicting the concept of a void. The universe exists because of complicated interactions between numerous fields and particles. The interplay of quantum fields, virtual particles, and dark energy assures that the universe is anything but an empty emptiness. Instead, it is a complex and dynamic system in which energy and particles are always interacting and evolving. Curiosity and a desire to explore the secrets of existence drive our search for understanding the cosmos and its beginnings. As we investigate these questions, we confront numerous unknowns and hurdles. The more we investigate, the more we understand how much there is still to learn. We must be open to new ideas and theories in order to better understand the cosmos. While current models and hypotheses provide useful insights, they do not represent the final word on the nature of reality. Thanks for watching. Stay tuned for more exciting ones.